Hey peak Hemmers, this is DW, and I'm going to walk you through some of the peak picking tricks that I've learned over the years, and I think it'll make this week's lab a lot more enjoyable. What I've got loaded here in Excel now is the CO data, the raw data file that you downloaded from Blackboard. And it's always a good idea just to see what the data looks like if you'll go ahead and plot that data. So I used Control Shift right and down to select the whole data set. Come up here quickly and use this XY scatter with straight lines. So that's what the data set looks like. I don't like it being down here at the bottom, so I'm going to hit Control X, Control Home, and Control V. So now my plot's up there where I like it. I don't like these thick lines, so I'm going to come up here and click line weight and make it a 1/4 point, and that's nice and clean spectrum. Okay, what we have here, the data is plotted in increasing wave number. If this was going to be turned in for a grade, I would want to flop that, because in infrared we like to plot the high wave number values on the left going to lower wave number values. But this information right here, these peaks right here, are the carbon monoxide peaks. And so these are what we're going to be peak picking. We get over to this area, we actually see CO2. It starts to take off towards CO2 spectra, and then we get in here, and this is another isotope of CO2, so that you might want to ask yourself, what would this signal be? But this signal here, these two P and R branches, are the carbon monoxide data that we're going to be analyzing. And so you'll need to peak pick these. But notice you don't just pick every maximum in a region, because there are some little peaks buried in between here. So we need to discriminate between the real signal of carbon monoxide and some of these other fake signals. They're not really fake, they're just not carbon monoxide, carbon-12, O16. So what's the quickest way to peak pick this spectra? I mean, if you were to try to get in here and hover, you would have a hard time trying to find the peak maximum. Although it looks like I hit it that one time, I got lucky. Okay, so right there, that little peak is the maximum for that one, and that's what we would pick. Let's see if we can find a better way. If we were to select this whole data series and do conditional formatting, we would see that the maxima, as we scroll down, we start to see some green areas and some yellow areas. These are the local maxima. And so this is alerting us that there's a maximum somewhere in this region. And so we have 225, 239, 235. So this is the maximum peak. So we could put an X there, or a max, or whatever you want to say to designate that spot as a maximum. And so we've picked that peak. We don't know what it is yet, but we've picked that peak. Let's try something else. Let's look at another way to do this. Let's come up here and type in a formula. You know, Excel has Boolean Logic. We can type in if-then statements. And so if we can say, actually let's do this looking over 5 data points, so or even 7. If this number is equal to the maximum in these 7 data points, then tell me it's a maximum. Otherwise, keep your mouth shut. Two quotes next to each other with nothing in between will just print nothing in that cell. And so we'll hit close parenthesis for the if-then statement and hit enter. We don't see anything because that data point's not a maximum. Get down on this corner and double click. And look, here of course is a sort of a double maximum. You have to pick to see which one of these is going to be the most valid data point to use, but you can see this picked several local maxima. Now this is a part of the spectrum that's noisy, and so we get a lot of junk. But then as we get down further, we can start, we can start seeing quite a few of those maxima are labeled. So I would use this method to identify the maxima. We're going to have a lot of peaks that are picked that are not actually the peaks you want, but I think it's good to capture a little bit more information than you want and then go through and get rid of the junk information. So one thing that we really want, we don't actually want the word maximum in there. We would like to have it pull this wave number value. And so let's do that. Let's, instead of the word max, let's have it return that cell there. And so that gives us that wave number value for the maximum. And then let's make this easy for ourselves. Let's do this again, but let's pull the absorbance value. And so if the absorbance is the maximum in that region, then return that absorbance value, else return nothing. Double click that, and now we have the wave number value and the absorbance value for all of the maxima in our spectra. And so then let's grab this column and copy it and scoot it over a little bit. Let's put it here and let's paste values so we get rid of those formulas. Paste values. And now I'm going to sort that column and pull all of those wave number values up and get rid of all of the blank spaces. And so now we have a table and we've reduced our data quite a bit. Now we have 250 data points to go through as opposed to 4,980. So I think that's a significant improvement to move from 4,000 data points to 250. Let's go ahead and plot this. Actually, we don't need all of those blank spaces, so let's come down here and just plot this data here. I'm going to copy that data and click this chart and hit paste special. New series. X categories are in the first column. Hit go. And then I want that data set to be markers only. So we're going to format that data series. So up here it says format selection. Come over here, we're going to put markers, marker options. Let's use one of the built-in ones. Let's do the little plus sign. And in terms of lines, let's use no line. And so those are all of the little maxima values that we picked. So this will help us identify all of the ones that we want to delete. And if we delete one of these that we want to keep, then that marker will go away and we know to hit undo. And so we might have to zoom in here to see which ones we want, but let's go ahead and zoom in from 2000 to 2050. So come up here, 2000 to 2050. And we see our first peaks that we want to keep are really not showing up until 2046, 2041. So really, let's see if we can't change this y-axis as well. We're going to go from, say, 0 to 0.4. Okay, that helps. So let's get rid of all of this junk up here. We can just kind of go down this column and hit delete, and those little markers will go away. See, isn't that nice? See, those are some peaks though. I'm going to undo on that one. Skip it. I don't want to throw away anything that might be a data point that I want to keep. So if it has a little peak on it, I'm going to keep it. to scoot my chart down. And so you see how this might help. Oops, I want to undo that. Scoot on to the next data point. Nope, undo that one. And I will come back later on with a particular plot after I've done this, and you'll see how we can clean this up even further. So after I've gone through and I've deleted everything except for these that are at the very tops of the peaks, I'm going to create this band assignment table. So let's go ahead and cut over to it. So I will have identified the frequency and the J value that goes with it, and I will label those either like P branch lines or R branch lines, and I'll end up with this assignment table. Reading in the lab, we've got this formula for if it's the P branch line, then we have the M number is minus J, or J minus 1, and then if it's the R branch line, it's J plus 1. So that gives us the M number. Then we create those 3 columns that we have that are talked about in the lab handout, and those are going to be our regression columns. But so let's not pay attention to this table just yet. Let's look at this tool here. So this is the assignment table, and you see how smooth the frequencies are depending upon the J quantum number. If you have a bad assignment, you see these little jumps and skips. And so if you have any noise like this in this band assignment table, then you've got some mistakes, and you need to go back and work on picking the correct peaks, because it's all about your peak picking. If you pick the wrong peaks and assign them the wrong frequencies, then you're going to have noise in this band assignment table. So you work until your band assignment table is this good and this clean. And I was able to get to P31. You may disagree with me and say it stops at P30 before it hits the noise, or you may be able to get P32. These last few data points are the most important for your centrifugal distortion constant. And also in the R branch, I was able to get to R28. You should aim for that. If you can't justify it and have to stop at R27, that's fine, but you really should look to see what the argument would be to justify R28. Maybe you can get to R29. Again, those extreme values are so important because the cubic dependence on those values gives you the centrifugal distortion constant. And so that the real goal of this lab is not just to get the bond length, but also to see if you can get a statistically significant measurement of the centrifugal distortion for this molecule. So once you finish with the peak picking, that's the main point. As far as the main, I would say the main amount of labor in this lab. Then you get to the assignments, and once you've assigned the P and R branches, you generate your M series. The whole reason we're using this M quantum number is so that we don't have to do 2 linear regressions. We could do a linear regression on the P branch and one separate one on the R branch, but it'd be nice to put it all into a single linear regression. Now, what is a linear regression? Well, it is a way to take the polynomial equation or any kind of linear equation, algebraically linear, where you have coefficients times some polynomial. And that's what we have here. We have BE times 2M minus AE times this value plus or minus DE times this value. And you can see that is in the lab handout. Now, if you will take these values here, these values, this function is what generates these frequencies. It's the theoretical model for these frequencies. And so the frequencies depend upon the M quantum numbers. And so when we do the linear regression, we come up on the data ribbon. We come over here and hit the data analysis tool. And if you don't have that, then right click on anywhere on this area where you're not clicking on a button, and see this customize the ribbon, and you come down here to add-ins, and you want to find this analysis tool pack. And when you go to add-ins, analysis tool pack, and hit go, then it allows you to select the analysis tool pack and the solver add-in. You want to add both of those into your Excel and hit OK. And then these two buttons will show up. We don't need the solver today, but we do need the data analysis button. So you click this and it gives you access to a lot of new data analysis tools. One of those being regression. So you click regression, hit OK, and now we have some choices. It's doing a regression to give you the coefficients of your model, and so we need the y values. The y values are our frequencies. So I click the first one, hit Control Shift down, and that selected the whole column. And then I come back up to y range, and to the x range, and these are the x values. These three columns. If I select three columns, I'll get three coefficients. The three coefficients of this column are BE, AE, and DE. So I click here and go down, and that's my x input. I do not want to click constant as 0 because we want to model the constant. We can create a new worksheet ply, meaning another sheet, and I'm going to call this trial regression. And that's it. So here's my trial regression. I like to clean everything up by clicking this top corner and then double clicking the column divider, and it spreads everything out. Now these are the four values for that equation from the lab handout. So let's find that equation. It's this one right here. And so we modeled it versus 2m minus 2m minus m squared and minus 4m cubed. And our four coefficients for that model are the vibrational frequency from level 0, the equilibrium rotational constant, the vibration rotation coupling constant, and the centrifugal distortion. So here are those four values. In fact, I could probably put this is the vibrational frequency, rotational constant, alpha, or I'll call it the rotation vibration coupling, and centrifugal distortion. So these are the values. So that's the vibrational frequency for carbon monoxide. This is that rotational constant, which we will turn into the bond length, and then the vibration rotation coupling, and then the centrifugal distortion. So what we're looking for are several things in a linear regression. We want to see the magnitudes of our coefficients, but also the standard errors. So this is the uncertainty in that. And you see it's quite good. It's in the third decimal place. This is the uncertainty in our rotation constant, and it's also very good. It's in the fourth decimal place. This is the vibration rotation coupling constant. This is now 10 to the minus 5, so it's down in the fifth decimal place. So we have 0.01750 plus or minus 1 in that fifth decimal place. And then here, this was a very small constant. Centrifugal distortion is 6.2 times 10 to the minus 6, but the standard error is at times 10 to the minus 7. So we've got essentially one significant figure plus one certain digit plus one uncertain digit. These p-values, we'll talk more about this in class, but this is the probability that this number here was due to noise in the data. Now think about that. The probability that this vibrational frequency came from noise in the data. And you see it's quite a small probability. It's 10 to the minus 268. This is the probability that our rotational constant came from noise in the data. In other words, the null hypothesis is that the rotational constant is 0. It came out as 1.9. What is the chance that that's really just 0 statistically because of the noise in the data? Well, the chance is 10 to the negative 172. Okay, this is the probability that our rotation vibration coupling constant is statistically 0. Well, it's 10 to the minus 129, and this is the probability that our centrifugal distortion constant is essentially 0 or not statistically significant, and that's 10 to the minus 38. So we have fantastic p-values because I was very, very careful in peak picking my data. If you get p-values that are large, then you need to go all the way back to the beginning and find the 1 or 2 peaks that are not correct, and you need to change them and update your formula and then redo the regression and see how it turned out. It's not that bad. Normally you can find the 1 or 2 data points that you're unsure about. If you will change that assignment, then you come back here and you'll get clean up your p-values. The last thing to do is then convert this data. Let's see, let's go back. Is then to take this standard error and these coefficients and compute the bond length, the vibrational frequency, the force constant, and all of those different things. Using the data, the physical constants from the CRC or the NIST, and so and also computing the relative standard deviation, the CV, the coefficient of variation, comparing that to literature values and computing the percent error. So you can do all of this with the skills that you already have. You can ask your TA or me for help as well. So that's a quick rundown on some strategies for quickly peak picking your data. Okay, great.